Hey, Dr. Clark, finishing up this second half of this video, jumping into curl. Let's get started right away. So as I mentioned before, curl talks about the rotational aspects of a vector field. That's quantified mathematically by this equation. It comes from taking the cross product of the gradient operator with a vector field. So remember, the divergence came from taking that gradient and dotting it with the vector field. Well, curl comes from taking the gradient and crossing it with the vector field. Mathematically, you see this as taking partial derivative, the y partial derivative of r minus the z partial derivative of q times the vector I, and then the z partial derivative of p minus the x partial derivative of r times the vector j, and then the x partial derivative of q minus the y partial derivative of p times the vector k. And so what you're noticing here is this I, j, k, those are vectors, so we're getting a vector. So the divergence of a vector field was a number, but the curl of a vector field is itself a vector. And what the curl is if the vector field is rotating at all, it would be rotating around some axis. So, if you imagine a vector field spiraling around like a tornado or something, there's going to be an axis of rotation around that rotation. And so curl just tells you what is that vector that vector field is sort of rotating around. And if the vector field isn't rotating at all, if it's just sort of moving, straight, then maybe there is no rotation and you get zero. But what you would get is the zero vector if a vector field was irrotational. And so not only do you get a vector that tells you which the vector field is rotating around some vector, but the bigger the length of that vector, the stronger the rotation. So there's sort of two pieces to a vector, direction and magnitude. The magnitude would tell you the strength of the rotation, and the vector itself or the direction would tell you the direction of the rotation. Okay, now this is hard to do. Imagine a 3D vector field, look at it and say, well, what's the curl? Well, it's kind of hard to pick it out. Mathematically, it's just a matter of doing this computation, but unless you've got some very clear rotation, it's not obvious to me how you would sort of say where the curl is. But in a 2D vector field, now come back here and think, if it's a 2D vector field, then this r would be 0. And so in a 2D vector field, this r is 0, so this is going to be 0, and this is going to be 0. And the z derivative will be 0 because these functions wouldn't depend on z, so that would be 0, and that would be 0, which means you're going to get 0i plus 0j plus something k. And that tells you that in a two-dimensional vector field, the curl is always coming out of the vector field in the k direction, and of course it would be rotating around the z-axis effectively, or a vector parallel to the z-axis. And so maybe here you can see it's kind of rotating around this point. So you would expect the axis of rotation to be the k vector, and then the stronger that rotation is at that point would tell you how big the magnitude would be. And maybe over here where the vector field is just kind of moving in a straight line, boop, 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 maybe the curl would be 0 there. But here where it's rotating, you would pick up curl. And of course, the curl could be negative if it was going clockwise. It'd be positive if it was going counterclockwise. So that's a sense of what curl is. You can see it in a 2D vector field, harder to see in a 3D vector field. Of course, you can always just do the mathematical computation as well. And one last thing, well, let's take an example and see how you might actually compute it. So let's just take this vector field here. It's 0, z squared minus y squared, and then negative yz. Now this one is 0 in the p component, so the vector field is living in the yz plane, so to speak. So that means it's a two-dimensional vector field. It just happens to be in the yz plane. So the curl should be going around the x-axis, And when we get to the final answer, you're going to see that I is the only thing left. It has a quantity and then the I vector. So that's exactly what's happening. How did we get there? Well, we're going to take this formula, the grad crossed with f. We had it in the slide before. We take the y derivative of negative yz. That would be negative z. We take the z derivative of z squared minus y squared. That would be 2z, so that gets subtracted, times I. Z derivative of 0 is 0. X derivative of negative yz is 0. X derivative of z squared minus y squared is 0. And the y derivative of 0 is 0. So those are all 0, and you just have negative 3z I. And so you can kind of see how to compute it mathematically. It is a cross product, so actually if you go and just take the cross product formula, the ijk, and just put in these derivative operators dx, dy, and dz into those spots, and then you just start doing the cross product as you normally would, where you'd say, okay, I've got the I vector, and then I have y derivative, and then z minus the z derivative, and then I've got j vector and x derivative minus 0 there, and then the k vector, and then x derivative and y derivative, right? You actually will get the same answer. So this, you don't have to memorize this formula if you don't want to, because you already know your cross product formula from before, and so that's kind of a nice little feature. A couple little items that's interesting. If you have a conservative vector field, so that's a vector field that comes from a potential function. That is, the vector field is the gradient of some potential function. It will turn out that the curl of that vector field will be 0. So conservative vector fields do not have curl. And if you think about, say, gravity, everything's pointing in towards the center. There's no rotation. It just all gets sucked in by gravity. That's an example of a conservative vector field. A radial vector field would be irrotational. So curl measures how much rotation is happening. The other thing is, if you started with if you take any vector field and take its curl, so let's say this is the curl, and then you take the divergence of a vector field that's made from curl, you would also get 0. So the divergence of the curl is 0 for any vector field. Curl essentially tells you how things are rotating. It only tells you about the rotation. So that means when you start looking at divergence, there isn't any divergence left because you were just sort of looking at curl. So the divergence of the curl of any vector field is 0, and the curl of any conservative vector field is the 0 vector. So those are a couple interesting things. We saw a couple examples there, how to do some computation, and we saw kind of thinking about what does this mean. And so hopefully that helps you with curl and divergence.